What I'd like to do today is talk a little bit about cholera. And by way of background, I'm an infectious disease specialist, as I've mentioned. I also direct the Emerging Pathogens Institute at University of Florida, which is a freestanding research institute, multidisciplinary, that focuses on things like pandemics. Now, we've been up to our ears in COVID over the last 2 years, needless to say. But much of my career has been focused on cholera. In fact, a lot of my life has been entwined with cholera. And so what I wanted to do today was talk not about the newest of the great pandemics, which is COVID, but the oldest of the great pandemics, which is cholera. And just to provide a little bit of background, the ancestral home for cholera is the Bay of Bengal. And when I showed these slides to my wife, she said, you're going to have to show a map to show where the Bay of Bengal is. And again, this is India along here, Burma, Thailand. The two key cities are Calcutta and Dhaka, which are actually very close together. This is the delta of the Ganges and Brahmaputra rivers, the great rivers of India. And it is in this area, in the delta of the Ganges and Brahmaputra, that cholera had its home and where it continues to have continues to be its source. To provide just a little bit of background for those of you who may not be familiar with this disease, it's caused by the bacterium Vibrio cholera. It is free living in environmental and estuarine areas. Primary transmission is by water, and it is quite capable of causing global pandemics, often leaving behind little pockets of endemicity, which again is, for me, it's been fascinating to watch COVID, because many of the things that we have learned with diseases like cholera, we are seeing replicating with COVID. As I tell my students, cholera is actually a very simple disease. When you get cholera, you get massive diarrhea. You may pass as much as 1 liter of stool per hour. This rapidly results in dehydration, volume depletion, and circulatory collapse. People can die within 4 hours of onset of symptoms. It is a devastating disease. It is also a disease which is, in many ways, very easy to treat. As long as you put the fluid back in, the patient's going to do fine. This bacterium doesn't get into your bloodstream. It really doesn't do anything else. It just causes massive diarrhea. This is the cholera treatment area at the International Center for Diarrheal Disease Research in Bangladesh. This is an older slide, but this is still the way things look. Basically, these women are laying on cholera cots. For those of you not familiar with cholera cots, basically it's sort of like a camp cot, rubber, and it's got a hole strategically cut right there in the middle. And essentially, when you have cholera, you are just passing effortlessly vast amounts of fluid. And so the women are laying here. There's the bucket underneath. That's what catches the diarrhea. And the nurse goes around every 15, 20 minutes, half an hour, sticks a ruler in there and measures how much, what the volume out is. And essentially, as long as you replace 1.5 times the volume out with what's going in, the patient does fine. And so the key is to replace the volume, and essentially that's done with intravenous hydration and also with oral rehydration. Now, what causes all these nasty problems? It's something called cholera toxin. And again, I'm not going to get into great depth in this except to note that there was a volunteer study, which I'm sure will never be replicated, where a volunteer was given 25 micrograms of purified cholera toxin. And they proceeded to have a 20-liter diarrheal purge. Volunteer did fine. Again, under controlled circumstances, as long as you're replacing the fluid, the patient does fine. But nonetheless, I think it gives a feel for the incredible power of this particular toxin. Essentially, what it does is shut down the intestinal cells so that it will excrete fluid, but it can't absorb fluid. But the key thing which is an actual relatively recent observation, is that cholera toxin does not affect glucose-mediated transport. And that may sound like some sort of fairly minor note here, but in actuality, it turns out to be incredibly important. Because if you give somebody in the middle of a cholera purge salt water with salt to try to replace their fluid, it's going to go straight through as diarrhea. But if you add sugar to that, then the sugar through the glucose-mediated pathway will be able to allow them to absorb fluid. And this serves as the basis for oral rehydration. And in fact, the person who was responsible for this observation was this guy here, Commander Robert Phillips. This shows him in the Abyssinia Fever Hospital in Cairo in 1947. And because of his studies and studies of other individuals working with him, the concept of oral rehydration was really promulgated. And again, it seems so silly. All you have to do is just add some sugar to the salt water. And there were traditional therapies which did this but didn't really realize what they were doing. But the actual widespread use of oral rehydration was, as pointed out by this Lancet article, the discovery that sodium transport and glucose are coupled in the small intestine so that glucose accelerates absorption of solute in water was potentially the most important medical advance this century. I agree with that statement. This has saved more lives than really anything else we've done in medicine over the last 100 years. All right, so let me just talk a little bit about the history of cholera. Basically, as far back as you go in records, you find descriptions of diseases that sound very much like cholera. And again, here you can see one from a text from Tibet from 800 AD. The various vessels secrete water so that the body becomes empty. The jaw kills invariably. Its first signs are dizziness and most violent purging and vomiting. And there is actually a Hindu goddess of cholera. There's also a Muslim goddess. And this is the Cholera Temple in Calcutta. So again, when you begin to get a disease that is having such an impact on society, you see the creation of temples. But I would note that we also saw this in the Western world. And this is actually from the city of Paris, the statue imploring heaven to take away the plague of cholera. Now, cholera first spread at a global level beginning in the early 1800s. The second pandemic, note that it was blamed on ships carrying Irish immigrants. You know, it's always the immigrants who are causing the problem. Hit New York, Philadelphia, came down to New Orleans, hit Charleston. Newspapers said that what you had to do to prevent cholera was to live a moral and temperate life. It was interesting, there was a physician in Scotland who thought, well, why don't we put some saline back in? And he did it with 15 moribund patients. Only 5 survived. He faced severe criticism and the treatment was abandoned. It may say something about our current approaches to clinical research. And it keeps going. Through the 1800s, there were a series of pandemics. We don't have the strains that actually caused these pandemics, so we cannot say with certain whether these were variants. But clearly, what we see is this recurrent pandemic pattern. I would note the third pandemic. This was when John Snow in London, who is regarded as the father of modern epidemiology, linked cases with sewage-contaminated water pumped from the Thames, and the local outbreak stopped with removal of the pump handle. As you note, as you go through here, as we get farther into the century, there is increasing application of public health concepts. This was a driver for the creation of the Metropolitan Board of Health in New York City. There was implementation of policies to identify and isolate cases. And, you know, again, what should be very familiar, isolation, quarantine, contact tracing, all of those techniques were developed back in this time period, primarily because of concerns about cholera and also because of typhoid. But then the variants start appearing. And again, when you're dealing with pandemics, there are always variants. This was the 7th pandemic, emergence of El Toro cholera. appeared first of all in 1937 in pilgrims from Mecca in Wadi el-Tor in the Sinai Peninsula. It was a variant strain. It subsequently caused explosive outbreaks in the Celebes beginning in 1961. And again, when you think about what causes a variant, what makes the variant spread, we have, it caused a large number of inapparent infections in mild cases, which might not come to medical attention, better environmental survival. It did not generate a strong immune response, so people were not as well protected, and the ability to replace existing classical strains within human populations in their environment. Again, sort of the key elements for what's necessary for a variant to spread. This just simply shows the global map, started in the Celebes, moved across to Thailand, which I'll talk about in a minute, across Asia, into Africa, South America, basically total global spread. And we are still today in the midst of the 7th cholera pandemic. We estimate that there are probably some 3 million cases of cholera per year, with variations depending on local outbreaks, and 100,000 deaths per year from cholera. This is not a disease that has gone away. It is a disease that is still very much with us. And now I sort of drop into the picture. My parents were missionaries, and at the age of 6 weeks, they took me to Bangkok, Thailand. This is the Hong Kong airport in 1952. For those of you who have visited Hong Kong recently, you may not recognize this, but this was the Hong Kong airport in 52. This is my mother, and she is holding me, 6 weeks old, and we are about to board a BOAC, British Overseas Airways Corporation, the predecessor to British Air, DC-4, which was the hottest, most modern thing at that time to fly to Bangkok. And again, this is me with my father at age 4. And then cholera hit. Remember that surge of cholera going from Indonesia up into Thailand? Well, it hit Bangkok. Bangkok was known as the Venice of the Orient. It had canals everywhere. This is a water organism. It likes canals. It liked Bangkok. And in 1963, when I was 11 years old, el-Tor cholera pandemic hit Bangkok. We didn't really know at that point much about the transmission pathways. There weren't lockdowns, but I think all of us now have experienced the sense of what a city is like when it's in the grips of a pandemic. There's sort of an eerie quiet. Nobody's out on the streets. Everybody's scared. People were dying. Literally, people were dying in the streets. Remember, this can kill in 4 hours. And so it was a very unique, and for an 11-year-old, this was extremely impressive. I would note that my mother was extremely, obsessive compulsive. All the water we drank was boiled twice and filtered. All the food was fully cooked. And we got a cholera vaccine booster every 6 weeks. The vaccine was lousy. We really didn't know what sort of antibody response we would get. And so the U.S. Embassy recommended that all U.S. citizens get vaccinated every 6 weeks during the peak of the epidemic. So we marched off to the embassy dispensary and got our cholera vaccine every 6 weeks. For those of you who worry about, should I get a booster in 6 to 12 months, here we're talking boosters every 6 weeks. Now, based on this, I ended up going into medicine. Again, this, as I said, for an 11-year-old, this was an indelible impression. Went to Tulane, got my master's in tropical medicine, spent a couple of years as a resident for Don Selden. And then Phil Makoviak at the time was at UT Southwestern. And on his recommendation, I went to CDC, where I was an epidemic intelligence service officer. This was the group that I was with, and I was in the enterics group. There I am. I'm not sure whether you can see this guy that well. That's Marty Blazer, the young Marty Blazer. This is Roger Glass. Roger Glass is currently director of the Fogarty International Center at NIH. And this is Jim Hughes, who was director of the Center for Infectious Diseases for many years. Jim and Marty are both ACCA members. It was an interesting group. My responsibility, I was given oversight, global oversight of cholera surveillance. And so shortly thereafter, I got sent back to Thailand, actually to the Rangsit transit camps. Some of you may remember there were over 500,000 Indo-Chinese refugees in camps in Thailand. And what we were finding out was that they were arriving back in the United States with cholera. We had 7 confirmed cholera cases in people on the airplanes. That's not good, because if you're in the middle of the Pacific Ocean and somebody starts a major cholera purge, they can be dead by the time they reach the US. And so, we had to find out what was going on. Anyway, not to belabor it, what we found, cases were associated with ice from local street vendors who were coming into the camps. It was also associated with crowding in the camps. Cases stopped when we increased the amount of floor space available per refugee from 2.6 meters squared to 4.6 meters squared. We also made sure that the airplanes carrying the refugees had oral rehydration and IV rehydration capabilities. We had been placing refugees on commercial flights. We stopped doing that. We decided we didn't want somebody in the middle of the Pacific on Pan Am suddenly, starting a major cholera purge and people trying frantically to resuscitate them. Shortly thereafter, I made a move to Baltimore. Probably the best thing that happened was that I met Deb, who was an intern in one of the Hopkins programs. And in Baltimore, I went to work for Mike Levine at the Center for Vaccine Development at University of Maryland. The idea was, how do we develop a good vaccine? Because there still was not a good vaccine. I remember this booster every 6 weeks routine. And so, you think about it, okay, if all this stuff is being caused by cholera toxin, then all you need to do is take out the gene for cholera toxin and you should have a beautiful live attenuated vaccine. Great idea. Science never works like it's supposed to, however. Actually, in some really elegant work done by Jim Caper, he came up with a strain called JBK70. When we fed it to volunteers, they still got diarrhea, a whole lot milder than they did with cholera toxin, but they still got diarrhea, indicating that this strain still had other actors, genes, that were causing diarrheal illness. I will not go through all of this, but basically, in 10 years of work, finally they came up with a construct called CVD 103 HDR, 91% efficacy against moderate to severe diarrhea in volunteer challenge studies. So we took it to a field trial. Field trials are the death of many great ideas. In the field trial, the efficacy was 14%. This is why when we talk about how miraculous it was that the COVID vaccine, is giving us the efficacies we're seeing, for those of us who have worked in vaccinology, this is what we're used to seeing. You take it to the field, it doesn't work. I will say, sort of as the rest of the story, there has subsequently been a great deal of work on killed whole cell cholera vaccines. Brad and Dave Sack from Hopkins were instrumental in this, and there is now an oral killed whole cell cholera vaccines. However, efficacy is 50 to 60%. Protective efficacy in kids less than 5 is only 38%. Not a great vaccine, but a vaccine. It's also kind of expensive. If you make it in the Western world, it's $6 a dose. Shankal coming out of India is 97 cents a dose. This is Uvicol. This is the South Korean version, which cost about $1.20 per dose. You just sort of chug down one of these little containers and you get protected. But then, at least for me, I got sidetracked with another variant. And again, when you work in pandemics, there are always variants. This was a variant that was called Vibrio cholera 0139, first seen in Madras, India, in October of 1992, spread rapidly. We all said, okay, the 8th pandemic is starting. But we actually focused a lot on this. Some of this is work from my lab. We identified the genetic changes, It just has a capsular polysaccharide. This was the structure. Everybody said, well, this is definitely going to take off. It's going to supplant the 7th pandemic strain. It didn't. After 1994, we've seen really no major outbreaks of Vibrio cholera 0139. Why? Why do some variants work and other variants don't work? And in this case, this was before we had the complete genome for Vibrio cholera, which didn't come out until the year 2000. So we really didn't know that much about the genetics, but we really started looking at other issues like, perhaps environmental impact. These are studies that I did in collaboration with the Sack brothers from Hopkins, Rita Caldwell, looking at environmental impact of various environmental factors on occurrence of cholera in Bangladesh, both O1s and O139s. And, there was a suggestion that the environmental conditions really pushed these strains forward, but we still didn't understand it that well, and in particular, we still didn't understand, we didn't look at the underlying genetics. We did have a general idea of cholera transmission pathways, and sort of the model that we were working on and that I think continues to be valid is that you've got Vibrio cholera in the environment. It has an environmental reservoir. Environmental parameters impact the amount of Vibrio cholera in the environment. It spills over into cholera infections in humans, and then what you get is rapid transmission within human populations, due in part to one of the things that we worked closely with was the idea of a hyperinfectious syndrome. Freshly passed cholera stool is much more infectious, much easier to cause disease than cholera stool that's been sitting around for a day or so. So if you really, get cholera, exposure to cholera stool just out of somebody else, all the right genes are turned on to make it really go crazy. But then at that point, I ended up moving to University of Florida to work on the Emerging Pathogens Institute. Again, this is our institute, the University of Florida campus. The stuff with Bangladesh was starting to wind down. And then there was the Haiti earthquake. January 12th, 2010. There was almost total destruction of the public health infrastructure, including water and sewage. University of Florida was part of the initial response. This is Mike Perry, who's Dean of our School of Public Health, getting out of one of the Army helicopters. You can see all the various activities, staff, students. And as we got further, into Haiti, one of the things that became obvious was we really needed laboratory capabilities. And so one of the things we did was build our own field infectious disease laboratory in Haiti. I will just mention in passing, when the lab was initially opened, Jimmy Carter was working a few miles away with Habitat for Humanity. And we asked him to come and say a few words. And his handlers said, oh, he can't be bothered. Maybe he'll drop by briefly. Well, he came by. He ended up speaking for half an hour brilliantly on international research and its impact on global public health, and took questions for another 15 minutes. The guy was incredible. So, regardless of your political feelings, it was, a brilliant presentation. And we also developed an overall research capacity within Haiti. This is actually, we built a BSL-3 lab there. This is some of the clinics we served. This is part of our UF group doing the gator chomp outside our lab. This is myself, my oldest daughter, Amy, and Deb in front of the guest house at one of the areas where we worked. And then cholera hit. In October 21st, 2010, the first case of cholera was seen in Haiti. And it occurred along the Artibonite River. And what appears to have happened is that there was a Nepalese peacekeeping camp of Nepalese soldiers who were peacekeepers, who were staying in a camp right on the Artibonite River, and they were dumping raw sewage into the river. And apparently one of them brought a Nepalese Vibrio cholera in their stool, asymptomatic carriage, and the strain rapidly spread along the Artibonite River and then from there into the surrounding area, and then rapidly across the entire country. Ultimately, there were close to 1 million cholera cases out of a population of 11 million. Because we knew about oral rehydration, deaths were lower in the 10 to 20,000 range, but again, probably higher than that because of the lack of medical infrastructure. There were, again, literally bodies in the road. It was an incredible public health disaster. Now, this just shows some of the modeling that we were doing at the time. And I, again, will not get too deeply into this other than to say, if for those of you who are now hopefully familiar with R sub naught, basically the force of infection, what we found is that we're in the area where it first came in, Artibonite, the environmental pressure force of infection was very high. But then once it moved into the other parts of the country, the major, the force of infection, the R sub naught for the environmental component was much lower. In contrast, the human transmission became the key element by which it was transmitted. And again, these are just some of the studies we did. Here we actually got GPS coordinates for cases through working with some of the nonprofits in the area. And again, this is not live, but if it was, what you would see is that the cholera moved right down the main highway, spreading directly off the highway. It then moved back into the countryside, and then it moved into the rivers. Haiti has rapid flowing rivers from the mountains. 70% of Haiti is mountains where you can't grow anything. And so there are these rapid mountain streams coming down. They got cholera in them. But this is a very different environment than what we had been studying in Bangladesh, where we had the languid Ganges and Brahmaputra. Here we had rapid mountain streams, but still we had cholera. We did work in Port-au-Prince, again, looking at the impact of cholera within these urban settings. Again, a lot of this is work that was done by Andrew Curtis at Case, who's one of our key collaborators. But for the first time, we had the genetic ability to look at the strains in the epidemic. And essentially what this is, it's a phylogeny that shows strains from the very beginning of the epidemic in 2010. And this is the backbone. Essentially what happens is the strains, and you're in the middle of a pandemic, the strains undergo ongoing evolution. And so I think the main thing to emphasize is that when we think about a pandemic, we tend to think of it as static. You've got disease X. In reality, these bacteria or viruses are constantly changing. And what you see here, again, is that as you move up this curve, you have certain strains, lineages that drop out, that die out. The purple ones are in humans, the green ones are in the environment. Here, it's primarily passage through humans. All of a sudden now the main line of passage is going through the environment. So there are environmental strains. Again, here, this environmental lineage dies. These continue. These then get back into humans. Then it gets back into the environment. I think the main thing to get across is this idea of the dynamic, of the evolutionary dynamic that is going on constantly within these strains, and which is going on constantly in strains with COVID, obviously as well. This is not the creation of new variants, because the changes were small step-by-step changes. But these are the types of changes that lead to the emergence of variants. And then this is basically what we saw in terms of the environment, human. And then in modeling, it looked like things were going to continue unless we really heavily vaccinated. And actually a group of us from Harvard and Hopkins and Florida worked with the Fogarty guys, put in some strong recommendations for, massive countrywide vaccination. Wouldn't have cost that much. 11 million people, $1 a vaccine, 11 million bucks. Not much to stop an epidemic, and that's what the model suggested we needed to do. The government said they didn't have the resources to do it. They didn't, and they had some advice from investigators from France who said it's all going to go away anyway, don't worry about it. Well, it turned out we were wrong and they were right. It did go away. And slowly, actually, by this time, we are really seeing no more cholera in Haiti. And, the question is why? Why did the epidemic stop? What happened? And what seems to have happened is that The strain underwent sufficient evolution, probably within the environment, to no longer be able to actively compete within the environment. And it died out in the environment and it died out in the humans. But we still don't know all the details. I've got 2 postdocs working on this right now. You know, ask me in a year or 2. But cholera disappeared. But, and, you know, cholera wasn't there, but where was cholera? Well, in actuality, Africa had become the hotbed for cholera, with 2 major hotspots. One at Lake Chad, and we started work there with a grad student from Cameroon. Actually, Dave Sack was working up from Hopkins, was working up in Chad. Problem is, Lake Chad was a little bit dicey. Our primary collaborator there got kidnapped by Boko Haram, you know, by the terrorists in that area, and we decided we really didn't want to stay around. So we moved over to the Albertine Rift Valley area with Democratic Republic of the Congo. And this is the Albertine Rift, Lake Kivu, Lake Tanganyika. Goma was the hotbed of cholera. It had consistently had cholera for over a decade. And so we started doing work in Goma. This is Goma. Goma has an active volcano. Remember, this is the Rift Valley. This is Mount Nyiragongo, looking over the city. It is actually a beautiful area. This is a little restaurant on the side of Lake Kivu, but there are not that many beautiful spots. This is a river leading into Lake Kivu. You can see they're using it for washing and all sorts of other things, garbage along the lake. And if you want to get your water, you get this guy to dump a jerry can down into the lake and pull it up, and you take it home. Probably not the best water source, but it's a water source. This is the cholera treatment center that we worked with there. We are working with Emilabo, which is the provincial laboratory where we are also again in collaboration. This just simply shows the map and the hotbeds of activity within the city. It's a city of about 750,000. Here, what was interesting was that again, well, first of all, this shows the entrance of cholera. It came in back in the 1980s, part of the 7th pandemic. Initially came from India, dropped into a variety of, several countries. Rwanda, from Rwanda spread into the Democratic Republic in the area in which we were working, and as well then spread back into Rwanda. So this looked like it was becoming an endemic zone for cholera within Africa. But what was interesting was that when we really started taking it apart, what we found was that there was a bacteriophage that was unique to this area, a variant bacteriophage. Bacteriophages are viruses that kill the bacteria, the cholera bacteria. And they are well known and well recognized. These are bacteriophages from Asia and from Haiti. This was a new one. It was a variant bacteriophage. And actually, when you look at this is the phylogenate going up. The red strains are strains that have developed resistance to the bacteriophage. The green are ones that are sensitive. And you can see the bacteriophage keeps driving lineages, but those all die out. For some reason, only the sensitive lineages are able to continue. And again, what it suggests is that there may be a sufficient load on the bacteria to be able to develop resistance, that the sensitive strains are selected. Again, we don't fully understand what's going on, but it gets back to this idea that these strains are constantly evolving. Not only these strains, but the bacteriophage that attacks these strains. It is an incredible, ongoing, complex biologic system, and we are only just beginning to understand it. And then the volcano blew. This was May 22nd, 2021. These are from BBC. That's the volcano. Remember that shot, that nice peaceful shot of Lake Kivu I showed you earlier? There's the volcano. There are the people fleeing the city. Google Earth is pretty impressive. This is Google Earth, and this is the lava flow from the volcano. And you can see it just cutting like a knife into the heart of the city. 750,000 people in the city evacuated. We were evacuating our staff, needless to say. Actually, we had our chief laboratory technician from Haiti who had just come to Goma to train technicians in Goma. So we had to get everybody out. We were able to finally got her on a plane in Kigali to get back to Haiti. When we went, all universities have this emergency evacuation insurance. Guess what? It doesn't cover volcano eruptions. So at this point in time, and again, this was just a couple of months back. This was in May of last year. We are now operating again in Goma. But they're refugees. And, the government has set up refugee camps. This is actually a mapping of the refugee camp, the tents within the refugee camp. In June of 2021, just a month after the incident. This is January 2022. Again, Andrew Curtis from CASE has done some beautiful mapping here. You can see that the refugee camp is now gigantic. It has become much more established. And when you have refugee camps, what do you have? You have cholera. And so again, we have a cholera outbreak. In many ways, this sort of comes full circle. I started out my career investigating a cholera outbreak in a refugee camp. I am again investigating a cholera outbreak in a refugee camp. And so to sort of summarize some of this, a lot has happened since 1854 when John Snow removed the pub handle in London and stopped an epidemic. The link between contaminated water and illness is indisputable, highlights the critical importance of good sanitation, clean water, and strong public health policies. The observation that cholera toxin does not affect the glucose-mediated transport and associated global dissemination of information about oral rehydration has made it possible to drop case fatality rates to well below 1%. Cholera vaccines are available, but they're not optimal. And I think the biggest change in our understanding is that the understanding that Vibrio cholera is undergoing constant evolutionary change, driven both by environmental conditions and by bacteriophage, and that the impact of these changes on occurrence of illness and the emergence of pandemic strains, and in particular variant strains, is still not fully understood. We are just beginning to appreciate the complexity of these biologic systems, an understanding which is critical to long-term control of cholera and other pandemics. I think we will be seeing with COVID these same types of things. Again, these are complex biologic systems. Only as we begin to fully understand them will we be able to develop rational control strategies. So cholera, again, is the oldest of the great pandemics. It's been part of human history for millennia, and so long as there is war and famine and natural and humanitarian disasters, it will continue as one of the great pandemic diseases of mankind. This is me at the age of 3. For me, it's been all about variants, microbial genetics, and understanding the factors that drive evolution. And it's never as simple or as easy as you think it's going to be. And again, these are just some of the folks that were helped with some of the many studies that I mentioned today. And again, probably my greatest thanks is to my wife, Deborah. This is our family, our 3 daughters, 2 sons-in-laws, and 2 grandchildren. Actually, we now have a 3rd that didn't make the picture. So thank you all very much. And I think there may be a little bit of time for questions if anybody has questions.
That was really a great talk, Glenn. I'm David Dale from Seattle. I just would call attention to the role of Chuck Carpenter in the development of the fluid rehydration programs in Bangladesh. Chuck's name was on the board as having passed in the last year. It really was a great member of our association.
And again, I definitely should have mentioned him. He was a key person in terms of the implementation of oral rehydration. As I said, that from a medical standpoint, that was one of the great breakthroughs of the past century.
David Twerdy, Houston. I wanted to thank David Dell for that comment. As being a trainee of Dr. Carpenter's, I really appreciate that being pointed out. My question is the selection pressure that's going on as we move forward with cholera, and even in the past. You know, is there any of this? Is any of that related to any reservoir that we now know? Because as I learned about cholera, I understood that humans were the only reservoir. So perhaps I wanted to know if there was any more information about that. And how does the bacteriophage work to select variants between pandemics as well as during pandemics?
Again, all of this is areas that we're still studying. I think for me, what has become most impressive is the tremendous amount of evolutionary changes that are occurring in these strains just on a routine basis. You know, that backbone curve of what is the predominant strain at any given moment of time, and all the little variants that go off to go nowhere. And so I think we are just beginning to learn what creates that backbone. And again, what to us was actually very surprising in Goma was that, you know, we weren't seeing the environmental impact that we were seeing in Haiti. What seemed to be happening is we were seeing this bacteriophage, which nobody had ever seen before. Again, it didn't match the bacteriophage that normally accompany cholera. And so again, what we had here was an evolution of the bacteriophage, which is then now driving the evolution of the cholera. And it's probably all going on all the time. The same as what's happening with the coronaviruses. It's going on a regular basis. And every now and then you hit a certain combination of genes, and then you have a true new variant, which springs out, and that's when you get a new pandemic. But not always, because the O139 didn't take off. And I still don't understand why the O139 didn't take off. So it's an incredibly complex system. And one becomes humbled by working with these systems and seeing the complexities, and all your good ideas and hypotheses, you know, frequently go nowhere.
Mark Seidel, Boston, wonderful talk. In invoking one of the great aspects of this society is its broad base. So as a transport physiologist, I look at this problem as unrestricted chloride transport in the gut. And the question is, every once in a while in my field, we hear about, well, maybe why don't we inhibit the transport so that the bug is there and it's stimulating the hell out of the intestinal cell, but the intestinal cell says, well, I'm not going to secrete chloride, and we could get rid of the problem. Have there been any therapeutics that have been advanced along that line that have any promise, or has it just proven impossible?
So far, it has proven impossible. You know, I know there has been some work, but I'll also be honest and say that nobody has really come back and looked at that issue really in the last 10 to 15 years, when suddenly, you know, the armamentarium we have in terms of therapeutics has substantially increased. Yeah. And I think there are significant opportunities that may well be opened up in this area. And this is an area where I think there would be opportunities for some, you know, very important practical clinical studies.
All right. Well, thanks very much.
Jochen Reiser, Chicago. Thank you for really stimulating talk, and sort of like dovetailing what Mark has just said. I'm a nephrologist, so I'm always intrigued when there's like bulk elimination that happens in the body. And obviously the cholera is one example. And I'm really thinking that in the kidney, I could see this as nephrotic syndrome, which can be rapidly onset in infections. And so I'm wondering what we can learn from that, looking at the barrier function of bulk elimination, sort of toxins in the gut and in the kidney. And I think there's a lot of great science that's going along those ways. And then finally, when you talked about sodium glucose co-transporters, obviously SGLT2 inhibitors, finally after a quarter of a decade, we have new FDA-approved drugs in kidney disease. So really important with talks like yours that we get stimulated to think from one system into another. So thank you for that.
Thank you. And I am in total agreement. I think there's some great opportunities. And again, as I said, this is a disease of the present. I didn't show, right now, Yemen has the largest number of cases in the world. The Democratic Republic of the Congo has the second largest number of cases in the world. Yemen is an absolute disaster. It would be marvelous if we had things, therapeutics that could effectively be used in these types of settings.
Makoviak, Baltimore. Terrific, Glenn. Thank you. So when I was in Bangladesh as a student back in the 70s, there were a ton of first world investigators there. And almost none of them ever came down with cholera. And they were potentially exposed. The conventional wisdom at that time was that they were so well fed and generally healthy, and so that you had to have the combination of the infection plus moderately poor health to develop clinical cholera. And I wonder, could this be an explanation as to why these vaccines work so well under experimental conditions, but not in the field?
Yeah, I think so. I think probably one of, Mike Levine has had a phenomenal career, but I think probably the low point was this 14% efficacy of this vaccine that had taken a decade to develop. And it probably was a combination of what you're talking about, the underlying nutrition, microbiome, underlying immunity. We have not really dissected out what happened. But I think we've got tools today that we did not have even 10 years ago. And I think with the tools we've got today, I think there is going to be ample opportunity to look at some of these questions.
Thank you.
Wonderful talk. John Carruthers from University of Michigan. I was wondering if you can comment, this is my understanding. I mean, I always think of cholera as technically a self-limiting disease, but you die from the dehydration because of the massive diarrhea. But the binding capacity of this toxin is such that blocking transport, as our nephrologist had mentioned, is nearly impossible. So I was wondering if you can mention the binding characteristics of this toxin, which has to be essentially washed away by sloughing off the normal turnover of the lining of the gut, compared to something that could potentially block. You'd have to need something to knock that thing off, which I think is the impossible part. Is that correct?
That's correct. Essentially, it binds irreversibly, permanently to the cell, and the cell essentially lasts for 3 days? I'll ask my gastroenterologist. But until the cell sloughs off, it doesn't work. But then patients recover usually in 3 to 4 days if you keep them hydrated.
Right.
Because then again, what happens is they repopulate their gut lining cells, and it works fine. And again, that's what's so incredible about this disease. It's so simple, but absolutely devastating.
Yeah, I remember several years ago, I'm a gastroenterologist, and one of the students asked me, why don't you just give them antibiotics? I'm like, it won't work. It's a toxin. You have to teach them those types of things. So thank you.
Glenn, very nice. Bert DuPont from Houston. Glenn, before you were at Maryland, I was at Maryland, and we began doing some challenge studies of volunteers with Vibrio cholera to induce cholera. And we kept feeding more cholera to human volunteers, and more cholera, and more cholera. Finally, we got to 11 logs of Vibrio cholera, and the volunteers retched. They developed fever, a sort of an endotoxic reaction, and they didn't get cholera. And then once we began to give sodium bicarbonate and neutralize stomach acid, it was so simple at 10 to the 6 to produce cholera. It's stomach acid, I think, is the critical thing to allow people, and achlorhydria, hypochlorhydria is part of the way of life in people in the areas you're studying. And I think, I remember an EIS officer getting cholera in Bangladesh, Eli Aberton. So a healthy young physician getting cholera. But I think we thought the key was hydrochloric acid. And even when we looked at the ones that got cholera with sodium bicarbonate and studied the ones that did and the ones that didn't and did histolog stimulation, there was an abnormal pattern of parietal cell output in the subgroup that did get cholera with sodium bicarbonate. So I think it's pretty simple. Cholera is simple. It's not a complex disease, but I think stomach acid's big.
I'm in complete agreement. And again, I should note Bert's work has been absolutely critical in many of the studies that have involved enteric infections. So again, my thanks to him as well for his contributions to the field.